Hi, this is a video podcast for Stage 2 Physical Chemistry at the University of Plymouth, and is part of a series investigating the shapes of molecules and how this affects their spectroscopic behaviour. This podcast is devoted to the last two symmetry elements, the first of which is called a centre of inversion. It's time to consider some more complex shapes. Up until now, we've looked at the effect of symmetry elements and operations on a hexagon, which is a good representation of a benzene molecule. Let's take that benzene molecule and add a metal ion to its centre. Now we can add a second benzene molecule opposite the first. This is a representation of an organometallic molecule. In this case, it is bis-benzene chromium in the eclipsed conformation. This is a single molecule. I've only shown it in two halves to emphasise the structure of the compound. As such, any symmetry operation must operate on all parts of the molecule. You'll notice that our labels now go up to 12, but again, this is only so we can identify how the operation moves vertices, atoms, around to yield our indistinguishable state. If a molecule possesses the symmetry element called a centre of inversion, this always resides at the centre of the molecule. The operation consists of moving all points of the shape into the centre and then continuing in the same direction back out the other side until each point is the same distance from the centre that it was originally. In this case, you can see that each vertex of the hexagons has been swapped with their opposite number when viewed through the centre of the molecule. So vertex 1, which was on the top hexagon and at 12 o'clock, is now on the bottom hexagon and at 6 o'clock. The symbol for this element is a lowercase I. A bit of thought will lead you to the conclusion that a molecule can only have one centre of inversion, since the structure can only have one centre. In addition, we don't have to consider what happens when the operation is completed multiple times, because performing the centre of inversion twice yields a state identical to the initial one. In other words, I followed by I yields E, the identity element. To demonstrate our final symmetry element, I'm going to use the same molecule, but in a different conformation. Here's the lower hexagon. Note that it has been rotated by 30 degrees. If we now add the second hexagon, the two hexagons no longer lie one above the other. This is the case in the staggered conformation of bis-benzene chromium. Now, this single symmetry operation can be demonstrated in two steps, but it is important to note that neither of the steps is a valid symmetry operation on its own for this shape or molecule. The first step is a rotation of 30 degrees, or 1/12 of a complete turn. Don't forget that the operation must be performed on the whole molecule, so both benzene rings turn. Note that this does not lead to an indistinguishable state. Even without labels, we could see that the vertices have moved. The second step of this single symmetry operation is a reflection in a plane that is perpendicular to the axis we have just used to rotate the molecule. Using the nomenclature I explained at the end of the last podcast, since the axis of rotation lies in the vertical direction, the plane must be horizontal. Another way of putting this would be to state that since the rotation axis was in the Z direction, the mirror plane must be in the XY plane. Here's the mirror plane in question. I'm now going to take the mirror plane away so that you can see its effect more clearly. And here's the result of the operation. The two steps lead to an indistinguishable state. Again, it is only our labels that show the molecule has moved. This element is based upon a rotation, but it's not a proper one. Hence, this symmetry element, or operation, is called an improper rotation and is given the symbol of an uppercase S. We need to state the order of the rotation, just like we did with proper rotations, and in this case, the order is 12. This concludes our look at all the possible symmetry elements that can be possessed by a shape, or for our application, a molecule. In the workshop, we'll look at more examples and practice combining symmetry operations.